A function is a subset of the Cartesian product where every element of A appears in exactly one ordered pair of our function. Other than that, there are no real restrictions on what a function might look like, but there are some special cases to consider. So if A is a set 0, 1, 2, and B is some set of symbols, one possible function is, but here several inputs have the same output. But we could imagine a function where all the outputs are different, and this suggests the definition. A function is one-to-one or injective if whenever we have two ordered pairs in our function where the second components are the same, then the first components must also be the same. Equivalently, in perhaps more familiar notation, if f of x equals y and f of x prime is y, then x must be x prime. Another special case to consider occurs with functions like this. In this case, the codomain is all of the range. And this motivates another definition. A function is onto or surjective if for every element of B there is a preimage x. And finally, we may be both, so a bijection is a function that is both one-to-one and onto. So let's play around with this a little bit. Suppose A is this set and B is this set. If possible, find a function that is one-to-one but not onto, a function that is onto but not one-to-one, and a bijection. Now, we haven't specified which is the domain and the codomain, so let's see what happens if we make A the domain and B the codomain. In that case, every element of A must appear as a first component. So to make a one-to-one function, we just need the second components to be different. So a one-to-one function might be What about a function that is onto but not one-to-one? To be onto, each element of B must be a second component. But our choices for the first component are just 0, 1, or 2. So no matter how we place them, we'll need to repeat one of the components. Now we really should prove that, so let's think about this. Without loss of generality, let 0 be assigned to the components w and x. Then the function includes the ordered pairs 0w and 0x. But functions can't do that. We can't have a different second component for the same first component. Well, in generality, suppose A and A is assigned to both B and B prime, where B is different from B prime. Then the function includes these two ordered pairs, but this means it's not a function. Consequently, it's impossible for a function from A to B to be onto. Or is it? Well, it is, but what we've shown isn't actually a complete proof of the fact. There's a very important assumption we're making here, which is that we have to assign one element to two different outputs. Seriously, what's with all the birds? Could we make an onto function with domain B and codomain A? Then each component of A must be a second component. So we know what our second components are, 0, 1, and 2. And to be a function, I just need to make sure I select different first components. And so this is an onto function from B to A. Or is it? Remember, every element of the domain must be a first component of an element of the function. So we have w, x, and y, but we still need a output for z. So z has to be in some ordered pair, and we'll go ahead and match it up with, I don't know, something. Could we make a one-to-one function from domain B to codomain A? So again, in order to be a function, every element of B must be a first component of the ordered pairs. To be one-to-one, the second components must all be different. But since A only has 3 components, it seems that that's not possible. Notice that we were able to find a one-to-one function from A to B, but it seems impossible to find an onto function. And we were able to find an onto function from B to A, but it seems impossible to find a one-to-one function. So it appears we can't find a bijection between the two sets. Or can we? We actually can't, but we do need to prove it. And for that, we'll need to introduce something known as the pigeonhole principle.